We're going to solve this differential equation, which is cosine x dy by dx plus sine x into y is equal to 1. And we can write first in the standard differential form of the first order linear differential. This coefficient must be 1. So for solving it, we divide by cosine x. We get here dy by dx. We get here plus sine x over cosine x into y is equal to 1 over cosine x. That gives me my p of x is equal to tangent x. Sine x over cosine x is tangent x. And my q of x is equal to 1 over cosine x. I find my integrating factor. My integrating factor is mu of x is equal to e to power integral tangent x into dx. Integral of tangent x, you know, that's e to power minus ln of cosine x. Or we can write this equal to e to power ln of cosine x to power minus 1. Our e and ln are cancelled. We get here cosine x to power minus 1. And then we are having here this equal to 1 over cosine x. That's my integrate factor. Now I multiply my differential equation. This is my differential in standard form by 1 upon cosine x, and we'll get here the standard result we'll get here in this form, that d by dx into integrating factor into y plus integrating factor in q of x. So I'll get here the differential equation as d by dx of integrating factor is 1 upon cosine x into y is equal to the integrating factor into 1 over q of x. What's my q of x? My q of x is 1 upon cosine x. So I'll get here this equal to d by dx of 1 over cosine x into y is equal to 1 over cosine square x. I hope that you know this one, that 1 over cosine square x is secant square x. So I can rewrite this one. I can write here my d by dx of 1 over cosine x into y is equal to secant square x. We integrate both the side. We get here integrating both sides with respect to x. With respect to x. So what we get? We get here 1 upon cosine x y is equal to integral secant square x dx plus constant c. Now we have 1 upon cosine x. So we know the formula for secant square x is tangent x plus constant c. So we get here 1 upon cosine x y is equal to sine is equal to sine x over cosine x plus constant c. We multiply by cosine x, we get here y is equal to sine x plus c cosine x. That's my general solution. This is the general solution of my differential equation. If I given the initial condition, I can substitute and get the value of constant, and then we call it as a particular solution. I just want to give you an idea, and I take this as a note. We want to solve this differential equation by the method of exact differential equation. The equation given to me is y plus 3 plus 2x minus y into dy by dx is equal to 0. But it's not exact, it's not linear, because here y is repeating. So if we want to apply the linear differential equation, we make it linear in x. We multiply by d by dx, so we get here y dx by dy is equal to 3 plus 3 plus 2x minus y equal to 0. Now in principle, what I do, I will try to write the equation now in this form. This is my get here in x we having here py into x is equal to q of y. So we write in this form, and then this will be, now we can see this is linear in x. It was not linear y because y was repeating, but here linear x. So I divide by y. I get here dx by dy plus here we get here 3 upon y. We get here 2x upon y minus 1 equal to 0. We keep the term with x on the left hand side, take it to the right hand side. We get here dx by dy plus 2 by y x is equal to 1 minus 3 by y. So I can get here my py is equal to 2 upon y, and my qy is equal to 1 minus 3 upon y. So we can use this value to write our integrating factor. So our integrating factor will be mu of y is equal to integral p of y dy. So we can just substitute here, and we'll get here this equal to e to power integral 2 upon y dy, and this is equal to e to power 2 ln of y. I get e ln y square is equal to y square, and you can just complete it, this equation. I just want to give you the idea for that one. This is here note 1. I give you one more idea in these equations. And note 2, we're given here a differential equation, and again the integrating factor. I want to check that this is the integrating factor for the differential equation, and we know that if it's the integrated factor of the differential equation and equation is not exact, it will become exact. For example, I given here the verify that we're having here mu xy is equal to x is integrating factor of the differential equation. My differential equation is 3y squared minus 4x squared dx plus 3xy dy equal to 0. I want to check, is this the integrating factor for this one? What I do, I just multiply by x, and then we can have the new form of the equation is 3xy squared minus 4x cubed dx plus 3x squared y dy equal to 0. Now we check if this is exact, and if it become exact, then this means that that's the integrating factor. So I am having here mxy. My mxy is equal to 3x y squared minus 4x cubed, and I am having here my nxy. My nxy is equal to 3x squared y. I find partial m by partial y. X is taken as constant, so partial y is 6xy, and this will be 0. I take here partial n by partial x is equal to 6xy. Derivative of x squared will be 2x, and y is a constant, 3 is a constant, get 6xy. Now we can have here partial m by partial y is equal to partial n by partial x. That means this mu x is equal to x is integrating factor. So if it is making an equation which was not exact and making exact equation, so we say that's our integrating factor. That's another idea. And then we can solve this one also by method of first order linear differential equation.